Greetings and welcome to week 4 in geometry. As always, I have a warm-up question for you to get started with, so make sure you've got your math notebook out. And I would like you to try this in your math notebook. I should see this warm-up problem in your notes this week when you submit your week 4 notes. So let's take a look at this warm-up problem. This is a parallelogram, so I guess I should state that this figure A, B, C, D, it is a parallelogram. And I want you to use what you've learned about parallelograms, all the different properties, to help you solve for the measurement of angle BCD. So angle BCD. We want to find the measurement of angle BCD. So go ahead and click pause and try this on your own, and then when you're ready to check your work with mine, go ahead and click play. All right, so we are looking for, like I said, angle BCD, so this entire angle right here. Let me move that out of the way a little bit. There we go, it's covering up the measurement of this angle right here, which is 37. So we know part of the angle measurement that we're looking at, but we need to find the measurement of ACD. So we need to find this angle measurement right here, right there, to help us find the measurement of BCD. So how are we going to do that? Well, we've got this angle down here. This angle is there, 23 degrees. So we know this angle right here is 23 degrees. And we're going to use some knowledge that we learned back in first semester to help us find this angle right up here. So these angles are alternate interior angles. Remember when we had two parallel lines and intersected by a transversal? And we learned that alternate interior angles, such as this angle here and this angle here, are congruent. Well, these are a set of alternate interior angles. So that means this angle up here is also 23 degrees. And now to find the measurement of angle BCD, we're just going to add that 23 degrees plus that 37 degrees, and we get a grand total of 60 degrees. So the measurement of angle BCD, that entire angle, is going to be 60 degrees. So this entire thing is going to be 60 degrees. So remember, things that we learned in first semester can help us continue to solve things that we're learning about in second semester. All right, so what are we doing this week in geometry? We are going to complete 3 sessions this week. The first one is going to be properties of special parallelograms. So we are going to be learning about rectangles, rhombuses, and squares. So rectangles, rhombuses, and squares are all types of parallelograms, meaning that they have all the properties that parallelograms have, and then some. So then they have some additional properties that make them special types of parallelograms. So again, we're going to be looking at rectangles, rhombuses, and squares. Those are the special types of parallelograms we're going to look at. And then we're going to finish up with looking at, in session 8, at our last types of quadrilaterals we're going to be exploring in Unit 5, and that's kites and trapezoids. So let's go ahead and get started and looking at these special parallelograms and kites and trapezoids. So let's go back here. So since the Unit 5 test is coming next week, I just want to put that into a warning for you guys, or not really a warning, just let you know it's coming up, so that you can be working on any missing work if you have any, and also redoing any Unit 5 assignments. Remember, that is a great way to study for the Unit 5 test. And remember also that when we complete Unit 5, you can no longer do redos from Unit 5. So just a heads up that we are wrapping up the Unit 5 assignments, taking the test next week, which means next week will be the last week to redo. All right, so moving on to special parallelograms. So I introduced in the beginning of this recording a little bit about the special parallelograms that we are going to learn about. So let's take a step back. So Unit 5 so far is all about quadrilaterals, right? Everything that we've looked at so far has 4 sides. So everything that we've looked at so far is a quadrilateral. So parallelograms have 4 sides. So a parallelogram is technically a quadrilateral, right? Because a quadrilateral just has to have 4 sides. A parallelogram has 4 sides. So a parallelogram is a quadrilateral. It's just a special type of quadrilateral that has all those special properties that we've talked about and reviewed in this recording. Well, now I'm about to introduce to you some special types of parallelograms. So just like a parallelogram is a quadrilateral, these 3 special types of quadrilaterals I'm about to introduce to you are parallelograms. So what are those special parallelograms? They are rhombuses, squares, and rectangles. So squares, rectangles, and and rhombuses are parallelograms. So that's what I wanted to show you with this chart, is that all 3 of these special types of parallelograms, they are parallelograms, which means they will all have the properties of parallelograms and then some properties that make them specific to their shape. And we're going to talk about what those are. But I did want to show you this chart. So rhombuses are parallelograms. Rectangles are parallelograms. Squares, they're even more special. So not only are squares parallelograms, but a square has all the properties of a rectangle, and it also has all the properties of a rhombus. And we're going to go over what those properties are right now. But I just wanted to show you this flow chart that explains what each quadrilateral, how it can also be the one in front of it. So let's go on to the next slide. Here we go. So let's talk about all the properties of all of our new special types of parallelograms that I just introduced on the previous slide. So keep in mind, this is a cool chart because it's kind of like a hierarchy of special parallelograms and their properties. So keep in mind that all special parallelograms have all the properties of parallelograms that we've talked about. But what makes these other guys special? So rhombuses have all the properties of a parallelogram, and then more specifically, their diagonals, the diagonals of rhombuses are going to be perpendicular. They're going to intersect at 90 degrees. That's what makes that special, is that the rhombuses are a little different from parallelograms, or special. It's a special type because the diagonals are perpendicular. So the diagonals will intersect at a 90-degree angles, and the diagonals will bisect the opposite angles. So these angles right here, the diagonals will bisect those, so that from here to here we'll have the same measurement from here to here. What about a rectangle? So a rectangle, again, has all 4 properties of a parallelogram, and then its diagonals are going to be congruent. So the length from here to here is going to be the same length as from here to here. That's what sets a rectangle apart from just being a parallelogram. And then squares have all the properties of parallelograms. They have all the properties of rhombuses, and they have all the properties of rectangles. And then to be a square, squares are going to have equiangulars, or equiangular. A square meaning all angles are going to be right angles. and then all sides will be congruent. So equiangular means all angles are congruent, equilateral means all sides are congruent. So technically, a square can be considered a rectangle because a square has all the properties of a rectangle. A square can also be considered a rhombus because a square has all the properties of a rhombus. And then a square is a type of a parallelogram because it has all the properties of a parallelogram. Opposite sides are congruent, opposite sides are parallel, opposite angles are congruent, and the diagonals bisect each other. So technically, a square is a rhombus, a square is a rectangle, and a square is a parallelogram. A rhombus is technically a parallelogram, and a rectangle is a parallelogram. Again, keep in mind as to what the properties are. So you'll have some lessons this week that state all the properties of these special types of parallelograms. But what I really want you to take away is how a square is also a rhombus. A square is a rhombus because it has all the properties of a rhombus. And same with the rectangle. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. All right, so now that we have been introduced to the properties of some of our, or of all of our special, some of our special right parallelograms, such as the rectangle, let's see if we can solve a problem that involves one of our special types of parallelograms, which is the rectangle. So this is a rectangle. We are given that information. It is stating this is a rectangle, pictured below. And we're given some information. We're given some side lengths. We know that from M to L is 10, and we know from L to O is 24. And we know that NL, so one of our, the length of our diagonal there, let's get that in, is 26. So the length from N to L, that's our diagonal, is 26. And we want to find the length of MO. We want to find the length of our other diagonal, and MZ, so half of our diagonal. So what are the properties of rectangles? So since we're told that we have a rectangle, and we're dealing with the diagonals, so really let's hone in on the properties of diagonals of rhombuses. So what are the properties of our diagonals of rhombuses? I think I just said rhombus. I meant to say rectangle. If I said rhombus, replace rhombus with rectangle. I meant to be saying rectangle that whole time. So the rectangle, in a rectangle, we know that all diagonals are congruent. So we know that all diagonals are congruent. So we know diagonals are congruent, and we know that the diagonals of rectangles bisect one another. They are going to intersect and cut those into two equal parts. So if we know the diagonals are congruent and we know LN, well, LN has to be equal to MO because diagonals are congruent. We know the length of NL or LN is 26, so that means MO must be 26. So the length, the segment, the length of MO has to be 26. So we answered one part of our question. The second part asks us to find the length of MZ. So the length from here to here, MZ. So if the entire length is 26, well, we know then that MZ has to be, MZ, I meant to say, not MN. MZ has to be half the length of the entire diagonal, MO. So we know MO is 26, so if we take half of 26, that's going to give us the length of MZ. And what is half of 26? If you said 13, you are correct. So the length of MZ is going to be equal to 13. So we just solved this problem completely using the properties of one of our newly learned about special parallelograms, and that is the rectangle. I'm going to go on to the next slide, so if you need more time, go ahead and click pause. Quadrilateral, to add to our list of quadrilaterals. All right, the next quadrilateral we're going to learn about is trapezoids. So a trapezoid is a quadrilateral. It's got 4 sides, but it's defined as a quadrilateral with only one pair of opposite sides that are parallel. So only one side, one set of opposite sides that are parallel. So is a trapezoid a type of parallelogram? Remember, parallelograms have 2 sets of opposite sides that are parallel. So a trapezoid is not a type of parallelogram. It is not a type of parallelogram. Remember, parallelograms have 2 sets of opposite sides that are parallel, where a trapezoid only has 1 set of opposite sides that are parallel. And those are bases right here. So that is what makes something a trapezoid, is you have 1 set of opposite sides that are parallel. Now, a more specific type of trapezoid is called an isosceles trapezoid. And we've already seen this term before, haven't we? Isosceles. We talked about isosceles when we had isosceles triangles. An isosceles triangle was a triangle that has 2 sets of, or 1 set of, 2 congruent sides. Start over there again. An isosceles triangle had 2 congruent sides. Well, an isosceles trapezoid is a trapezoid that has congruent legs. So it has 2 congruent legs. So a isosceles triangle is different than just a plain old trapezoid because it has to have 2 legs that are congruent, where a normal trapezoid does not have to have any legs that are congruent, where an isosceles trapezoid is going to have a set of congruent legs. So remember, that tick right here lets us know that this leg and this leg are congruent. This arrow and this arrow lets us know that these 2 sides are parallel. So it's got a set of parallel legs, which makes it a trapezoid, and then more specifically, it has a set of legs that are congruent, which makes it more specific, a isosceles trapezoid. So we're going to go to the next slide where we're going to work on a practice problem and put to use some of the properties we've just learned. So if you need more time here, click pause. Remember, taking notes, drawing pictures, you should include pictures in your notes. Don't just copy down the words that explain what a trapezoid is or what an isosceles trapezoid is. Draw a picture. Pictures help us really see and understand more of what the terms mean. All right. We've talked about the sides of trapezoids, but now let's talk about the angles of trapezoids. So if a trapezoid is isosceles, and this trapezoid is an isosceles, how do I know that? Well, there's a tick here and a tick here, which lets me know that these 2 sides are congruent. So if we have an isosceles trapezoid, then each pair of base angles, so remember this is a base and this side is our base, each side of base angles will be congruent. So that means that angle A and angle B will be congruent. And then that means that angle D and angle C will be congruent. So notice there's 1 arc here and 1 arc here, meaning A and B, those 2 angles are congruent. Then I did 2 arcs and 2 arcs here, showing us that angle C and angle D are congruent. These 2 angles are congruent. Then if we were to add some of our adjacent angles, if we were to take the measure of angle A and add it to the measure of angle D, they're going to be supplementary. Remember, that means they're going to add up to 180 degrees. And then if we add our other 2 sets of angles that are remaining, angle B, the measurement of angle B plus the measurement of angle C, if we add those 2 up, we will also have a total of 180 degrees. Those 2 adjacent angles are supplementary. All right, so I'm going to go on to the next slide where we're going to put to use some of these properties to solve some problems. All right, so I've got a trapezoid. I know that because I've got 2 sets of 2 sides that are parallel. And then I've got another property here. Well, I've got a tick on this leg and a tick on this leg that lets me know that these two legs are congruent. Therefore, I'm dealing with an isosceles trapezoid. I've got an isosceles trapezoid, which we learned some properties about on the previous side, or the previous slide. I'm also given some information here. I'm given that angle S is 50 degrees. I'm given some information about this isosceles trapezoid. I have one of my angles is 50 degrees, and then I'm given the length of side RQ as 2.16, and then since I know RQ is 2.16, I know that SP would also have to be 2.16. So I'm just going to write that information in, and then I'm going to come back over here and look what the problem wants me to find. It wants me to find the measurement of angle P. So let me change colors here. So we want to find the measurement of angle P. We'll do that in orange. And then we want to find the measurement of all the other angles, R and Q, Q and R. So how can we find all these missing angle measurements when we're only given this angle measurement right here, angle S? Well, because I'm also given two side lengths, it allows me to determine that this is in fact an isosceles trapezoid. And once we know this is an isosceles trapezoid, we can use the properties that we just learned on the previous slide about the angle measurements of an isosceles trapezoid and the patterns that occur. So right away, can I find the measurement of angle R? So angle R is right here. Can I find that angle measurement? Well, sure I can. Remember, we learned that the base angles will be congruent. So I learned on the previous slide that the measurement of angle S has to be congruent to the measurement of angle R. Well, I know the measurement of angle S. It's 50 degrees. So if I know the angle measurement of angle S, don't I know the angle measurement of angle R? It would also have to be 50 degrees. So the measurement of angle R has to also be 50 degrees. So we found one of the unknowns. What about angle P? Well, what do we know about the relationship between angle S and angle P? They're adjacent angles, so they have to be supplementary. So supplementary means adds up to 180. So I know that if I take the measurement of angle S and add it to the measurement of angle P, it has to give me a total of 180 degrees. Well, now I could substitute in that 50 degrees that we were given for the angle measurement of angle S. We don't know the measurement of angle P, and we set it equal to 180. Now we've just got a basic algebraic equation, and to find the measurement of angle P, we're just going to subtract 50 from both sides. And I get the measurement of angle P equals 180 minus 50 is 130. So the measurement of angle P is going to be 130 degrees. So now, do you know what the measurement of angle Q is? If we know the measurement of angle P? Sure we do. The measurement of angle Q also has to be 130 degrees. Our base angles are always going to be congruent, so that means that the measurement of angle Q also is going to be 130 degrees. So we found all three of our missing angles using the properties that we learned on the previous slide about isosceles trapezoids. So I'm going to go on to the next slide, so if you need more time, go ahead and click pause. We're going to look at some more problems. Or actually, no, we're going to look at the diagonals of trapezoids next. We're going to look at the property of diagonals next. All right, so remember, a diagonal is when we start at one vertex and draw a straight line to the opposite vertex. That is a diagonal. So in an isosceles trapezoid, we've got a tick here and a tick here, which lets us know we've got a set of congruent sides, making this a isosceles trapezoid. In an isosceles trapezoid, the diagonals are going to be congruent. The diagonals are going to be congruent. So I just went ahead and added the points or the vertices of this trapezoid, vertices A, B, C, D. So this makes this trapezoid A, B, C, D. If we are looking at the diagonals, this quadrilateral will be a isosceles trapezoid if and only if our diagonals are congruent. So AC, the distance from AC would have to be congruent to the distance from B to D. And that, if we have that true, then we know that we're dealing with an isosceles triangle. An isosceles, or triangle, I meant trapezoid, not triangle. We're dealing trapezoids now, not triangles. So if we have opposite, or our diagonals are congruent, then we know we're dealing with an isosceles trapezoid. We're dealing with an isosceles trapezoid. So remember, if we're given the vertices and we want to find the distance from A to C, we would use the distance formula. So just a hint when you go to do your Unit 5 project this week. So let's now look at number 1. Let's look at this first example here, using diagonals. So if we are so we know we've got a 4-sided figure here. Then we've got one set of opposite sides that are parallel. So that means we're dealing with a trapezoid, not a parallelogram. And then we've got this tick here and this tick here that lets us know we've got one set of opposite sides that are congruent. So more specifically, we know that this quadrilateral is an isosceles trapezoid. Then we're given some information. We are given that JN, so the distance from J to N, is 10.6. I'm going to put that in there. And we know NL is 14.8. So what is the entire length? Do we know the entire length of that segment, JL? Sure we do. JL would have to equal, we just add together the two given values that we were given. And what do we get? 25.4. So now we're asked to find the length from K to N. We're asked to find the other length of the other diagonal. Well, since we know that this is an isosceles trapezoid, we know something about our diagonals, don't we? That we just learned. We know that JL has to be equal to KM, right? Well, since we now know that JL is 25.4, that means KM must also be 25.4. So KM is going to be 25.4. And we were able to determine that by now knowing that the diagonals are going to be congruent. I'm going to skip number 2. I'm running out of time here. I do want to introduce kites. So you're going to learn some more about trapezoids. You're going to learn about the mid-segment theorem. So if we draw a segment in a trapezoid, that's called a mid-segment, and you're going to learn a little bit about that on your own in the Schoology lessons this week. But I did want to introduce the last type of quadrilateral that you're going to be learning about, and that is a kite. So what does a kite look like? It looks like those kites that we fly up in the air. But it's got some properties about it that make it special, that make it a kite. So with a kite, we're going to have 2 pair of adjacent angles that are, or adjacent sides that are equal. So here we've got adjacent sides, those are equal. These 2 set of adjacent sides are equal. So if you have 2 sets or 2 pairs of adjacent sides that are equal, you're dealing with a kite. The angles are going to be equal where the sides meet. So that means this angle here and this angle here are going to be equal. So our non-vertex angles are equal. This angle here and this angle here are only 2 sets of congruent angles. This angle and this angle, they are not congruent. So we only have 1 set, and that's where our 2 unequal sides, our 2 sides that are not the same, that are unequal, where that vertex meets those sides, those are the 2 angles that are going to be equal. Your diagonals are going to meet at a right angle. So the diagonals will all meet at a right angle. So there's going to be right angles in every single one of those vertexes. The diagonals bisect each other. So we've got this diagonal bisects this one. It's going to cut it into 2 equal segments, and then the diagonals bisect the angles. So that means this angle here is going to be equal to this angle. Do it like 2 of them, and then these 2 angles down here would be congruent to one another. So I know I quickly went through those properties. You will see those properties reintroduced to you in your Schoology lessons, but I did just want to go over those really quick. Again, we don't have two sets of opposite sides that are parallel, so kites are not a type of parallelogram. They are a type of quadrilateral. And are we ready for the last slide? The key phrase assignment. So we don't have enough time to go through we didn't have enough time to go through any of the kite examples, but again, lots of great information in your lessons this week. All right, so our key phrase assignment question. You need to answer this question to get your points for watching the recording. You learned what makes a trapezoid different from a parallelogram by watching this recording. So I want you to tell me, how is a trapezoid different from a parallelogram? That is it. Remember, I'm here for help, and the only way I know what questions you have is if you are actively reaching out and asking me those questions. So please, if you have questions this week, send me a quick email. Let me know what your question is. Otherwise, have a fantastic rest of your week.